Hi, I'm Jimmy Lapping, psychologist and statistician, and in this video I provide an example of a single case design in the context of education and psychology by means of a worked example in the statistical programming environment called R. In a single case design, the same participant or subject is measured repeatedly on the same outcome variable of interest during a given time period. Depending on whether any manipulation and/or randomization occur, the design can be either observational, quasi-experimental, or experimental. In the case of the latter, experimental, both manipulation and randomization are applied. Although the term single case design is used for designs that follow the same subject or participant during a given period of time, this does not imply that a single case design study uses only one participant necessarily. It can be used with only one participant, as is often the case in, for instance, financial markets, when we follow one specific stock or commodity during a given time period. In the context of the social or health sciences, this kind of studies usually include, or at least usually should include, multiple participants. That said, to illustrate the potential of single case designs at the level of the individual participant, in this simulated example we deal with a single participant who completes 30 trials or scenarios of similar difficulty in a virtual reality game. Between each two trials there is 1 day of no trial. Each trial results in an integer score ranging from 1 to 12, with 12 indicating the maximum score or best performance. The first 15 trials are before training in this kind of situations that is practiced in the game and therefore serve as baseline period. The day after the first half of 15 trials ends is when the training takes place, and the day after, the second half of another 15 trials starts. The research question here is, does performance improve after training? Note that this is not a single case experimental design, because although there is manipulation, there is no randomization taking place here. If you are interested in examples of experimental designs and applications of this statistical modeling approach on such designs, you can contact me using the email address at the end of this video so I can direct you to an example. So to start, we need to prepare a data file in CSV format, which can be done, for instance, using Excel, or better, directly via the platform in which the game scenarios are played. So we can read the data directly in R using the read CSV function. Once we have defined the data file, the first line of code here, we define the variables and open the packages we are going to use for our analysis. The NLME package is what we will use for statistical modeling, as I will explain in a couple of minutes, and the ggplot2 package is what we will use to produce graphs or charts. In the remainder of this video, we will run through examples of code together so you can try this for yourself at home. So let's start with some visualization of the data. We do this using the ggplot2 package with the following code. You see a line that defines title, subtitle, and the horizontal and vertical axis, then a line that defines the data, that the data should be visualized as points with a given size, shape, and color, then a vertical and horizontal line in specific positions in the chart, then two lines that define that we want a chart with simple white background and no grids, then definitions of the units on the horizontal and vertical axis, and then some annotated texts on two specific locations on top of the chart. Since this is a video that you can pause at any time, if you feel that I'm going too fast in some of my explanations and you need more time to look at the code, for example, just pause the video and have a look at the code. Alternatively, if you want the example that I provide in this video, I can send it to you in the form of a text file via email, and you can contact me using the email address that I share at the end of this video. So when we run the 12 lines of code that we just saw, we get exactly this chart. What do we see here? Well, relatively better performance after the training compared to before the training. So now that we've seen the data, let us compare a few possible models for this data set. To start, we will run a model that is often referred to as the null model or model 0. A model that states no effects at all, training or time, it does not matter, they have no effects whatsoever according to this model. So simply a flat line indicating that we give the same prediction of performance for any of the 30 trials. Here we see an example of code. We use the package called NLME, which uses a GLS or Generalized Least Squares estimator and RAML or Restricted Maximum Likelihood. These are two default settings for this kind of time series that usually account for the features of this kind of data fairly well, at least in many education and psychology settings that I'm familiar with. Then you see we define a correlation type because the data that we are dealing with here is time series data from the same subject or participant. This is important because it means we should not use the kind of classical linear regression that most of us learn in a bachelor's or master's education or psychology program. That classical regression approach is not useful here. If we were to run that classical linear regression model on this data, we would effectively treat the data as if 30 randomly selected participants each completed one trial, whereas in fact we deal with one and the same participant who completes the full series of 30 trials with 2 days in between each trial. This creates a so-called serial correlation in the data that we need to account for, and in most education and psychology settings that I am familiar with, the combination of GLS and RAML in combination with the correlation type specified account for that serial correlation reasonably well. The P stands for autoregressive serial correlation, whereas the Q stands for moving average. I will leave the technical details between these two types of patterns for another video, but P equals 0 and Q equals 1 means that we are going to run a moving average model. It's a matter of taste. Some people might prefer a P1 and Q equals 0, which would be a first order autoregressive model. That's to some extent a matter of taste. Both models will provide roughly the same outcomes here. Most important is that you document which model exactly you have run, and well, if this was an article, you would also justify why, for instance, you have chosen a moving average model and not an autoregressive model, or vice versa if you were to choose for the autoregressive model. The other lines here I will not discuss in much detail, as well as more technical correlation types or other combinations of P and Q. I will leave them out of this video, not to end up with a video of 40 minutes. But I decided to include all these lines of coding because they are always a part of my analysis and include a careful inspection of the residuals, for instance, which is something I tend to do, by the way, under different correlation types as well. Run different correlation types, look at the distribution of residuals, which should look something like white noise or uncorrelated. I mean, the correlation between residuals will not be exactly 0, but there should be no noticeable serial correlation left once we account for the data in a reasonable way, the patterns in the data. More on that a little bit later. Okay, so next here the code for the chart, which is really almost the same as the code we saw for the previous chart, with the exception that the title has been changed and a line has been added to present the predicted scores according to model 0, which should be a flat or horizontal line, as we discussed before. And indeed, we see here the data and the predictions according to model 0. In other words, we see that model 0 is basically a bad model because it systematically overestimates performance prior to training, whereas it systematically underestimates performance after or post-training. It's the simplest model and typically a useful control comparison, a control comparison I always include in my statistical modeling, but for the kind of situations that I study, it is rarely the model to be preferred. Next, we run a model that we will define as model 1 and holds the main effect of time. Basically, this moving average model differs from model 0 in that instead of a horizontal line, it predicts that the score is a linear function of trial with performance increasing or decreasing over time in a linear fashion. So the code is almost the same as for model 0, just added trial to the model read. The first line you now see trial added to the model. And as we go through this example, you see that I indeed reuse a lot of code for both the model and the chart. This is how on a daily basis I save tremendous amounts of time on preparing the analysis. I spend enough time to prepare the data file in the right format. That, in combination with data screening to see that you have no rubbish in your data, or illegible characters in your data, such as letters instead of numbers. So I spend enough time on that. Really, that's actually most of the time that I spend on a job. So that I can use the same codes to really compare the same kinds of models on loads of different data files that originate from studies that use the same kind of design. No need for button clicks in menus, which you may have forgotten by the time you reopen your data file in a month from now. Simply open R and your text file that holds the script. And well, you just put pieces of that script into R and get your output. It is as simple as that. Here the chart that we are going to run for model 1, which is again almost exactly the same as the chart for model 0, just now that we changed the title to model 1 and ask for the predicted scores according to model 1 instead of model 0. And this is what model 1 looks like, visually much better than model 0, though it still feels somewhat uncomfortable because it seems we have two separate clouds of data points that do not really allow for a single straight line description. So let us have a look at a few other models. Model 2 will have the stage effect instead of the time effect. In other words, this model states that the difference in performance between prior and post-training is simply a function of stage or training, and that within stage there is no trend. Next, this is the code for the chart of model 2. Again, like model 1, the title is now changed. So the title is changed to model 2, and we ask for the predicted scores according to model 2 instead of model 1. But the rest of the coding is really the same. And this is the resulting chart. Looks quite nice and optically perhaps a bit better than model 1. Although one could wonder if the time trend within stage can indeed be summarized as non-existent or zero, which is effectively what this model does. No, it assumes no time trend within any of the stages, basically just a kind of constant performance within stage. This is model 2. So let's run another model, which we will call model 3, that includes both a main effect of stage and a main effect of time. The code is again almost the same as before, with the main difference that now we add both count and stage to the model formulation. And here the code for the chart, which is almost the same as for previous models. Again, just a title change, that we now ask for the predicted scores according to model 3. Yes, this model, let's see. This is what model 3 looks like, yeah? It a positive stage effect indicating better scores after training than before, and within stage a slightly negative trend. Now, when we look at the data, we may wonder if these clouds indeed are positioned such that the same time trend applies to each of the two stages, or that perhaps we need a model in which each stage has its own time trend. And yes, such a model exists. We can call this model 4. We will do that now, model 4. And you see that in the code we add the product term, count by stage, in order to define the so-called interaction effect, We also call this the full model or full factorial model because it includes both the main effects of stage and time, the two variables under consideration, and their combined or interaction effect. This is what the chart code looks like, really almost the same as before, but just with the title again changed to this model. So we now ask for the predicted scores, and we now ask for the predicted scores according to model 4. And this is what model 4 looks like, although it has in common with model 3 that it includes both stage and time effects. It also includes the interaction effect, as a result of which the time trend before training is no longer the same as the time trend after training. We see that before training there is a mild improvement, whereas post-training there is a mild regression towards slightly lower scores as time passes. Still, although I prefer to not to go into detail of that in this video for the sake of simplicity, the outcomes from the NLME package still demonstrate an improvement of scores after training, but we do see it fades a bit as time passes. Of the 5 models compared using formal statistical testing criteria, this would be the preferred model of the 5 models that we have compared for this data set. Now, are these the only 5 possible models that we could run on single case data? No, certainly not. For example, during weekends I run this kind of models and a wide variety of considerably more complex models on key data from financial markets, including stock prices as well as the prices of precious and industrial metals and commodities like oil and gas. But those time series have in common that, depending on the time frame I define, I tend to be dealing with hundreds and sometimes even thousands of data points for a single subject. For example, daily gold prices over the past 5, 10 or 15 years. You're talking about over 1,000, over 2,000, over 3,000 data points respectively. For such models, where we have both much longer time series and much more complex patterns with swift moves up and down across the time series, we will be able to and we will need to use more complex models. But for many situations in education and psychology, this kind of model will do the trick. Usually do the trick, and often there is not much more information to go beyond this kind of periodic or stage-wise linear models anyway. And for this data set, this last model that we are having a look at, model 4, which is stage-wise linear but includes both main and interaction effects of stage and time, provides a reasonable model for what is going on with the performance of this participant. Going back to the research question, we would say that indeed performance is better after training. Now, does this mean that there is a 100% cause-effect relation between training and performance? No. For better causal inference, we could, for example, use a larger sample of participants, randomize the starting point of training in this sequence of 30 trials and see if this increase of performance can be replicated in other participants, right after training, and also with regard to, for instance, the trends within each stage. But regardless of any direct causal attribution, it is the case that the participant here demonstrates better performance after training compared to before the training, leaving in the middle whether this improvement was exclusively an effect of training and or of something else. So I hope you find this video helpful in your attempt to understand the idea of a single case design and a possibly useful tool to model and visualize this kind of time series. And for any comments or suggestions for future videos, please leave a comment below this video or get in touch with me via lappinganalytics@gmail.com. Also, if you like this content, please hit that thumbs up or like button below this video, and even better, hit subscribe, because on this channel, which is really just a couple of weeks old, I share videos on this and related topics almost on a daily basis in a variety of languages, 9 languages thus far to be precise. Thank you very much for listening, have a great day, and see you soon.